so we're going to start talking about convex mirrors, and convex mirrors have the mirrored surface on that outside. So they're just the flip of a concave mirror, but the mirrored surface is on sort of the outside of the bubble, as it were. If you look, so this is in Holt Modern Physics on page 538. If you look at page 538, and this will be really useful to, I think, all of you, there is a chart of sign conventions for mirrors. It's hard to read from here. But, we've already talked about this. Positive is the front side of the mirror, negative is the back side of the mirror. P, which is where your object is. Oh, it wasn't recording. Well, that's lovely. P is always positive because if you put something behind the mirror, it doesn't make an image. If you think about this with your bathroom medicine cabinet, when you wake up in the morning and go look in the mirror in the bathroom, the stuff that's behind the mirror is not what you see. You see what's in front of the mirror, which is your smiling face or growling face or whatever you see in the morning. But it gives you, the conventions for Q of positive being in front of the mirror, negative being behind the mirror. It's pretty easy to remember, but it's there for reference. Now, I did figure out how, if you're using doceri to do mirrors, I did finally figure out how to draw a decent mirror in doceri using the circle function. So if you draw the circle and stick your little center in there, that's probably about as close to center as I can get, rather than attempting to use a portion of that circle and erase it and then it picks up the erasure and it doesn't do that, you just enlarge it and trace over part of that and then erase the circle from under it. And it's the only way I found that really works. I'll show you. Okay, so I've got this enlarged to the portion that I want to use. I'm going to make this a fatter line. I'm using a blue line just by sort of convention. Oh, come on. Oh, really? There. And I'm just tracing over the black line, and it's not perfect, but that's okay. Then I can shrink the whole thing. I can stick in a principal axis. And obviously I have to move my principal axis up a little bit. And my principal axis is not parallel. Oops, I think that's pretty close. And then I can just erase that, and I have a mirror. So it's not perfect, but it's better than I was able to do freehanding it. And it means that your radius is actually correct. Okay, so here's a convex mirror. The mirror side of this, the reflective side, is out here. What do you immediately notice about C? It seems like it's on the wrong side. No. The center of the arc is behind the mirror. The center of curvature for a convex mirror is negative. So, with a convex mirror, C is negative. Okay. What does that mean about F? Okay. With a convex mirror, the center of curvature is negative, which also means your focal length is negative. Because just like with a concave mirror, the focal length is where? Halfway. Yeah, it's the halfway point. So you're, and I'm sort of dummying it there, but there's your focal point. So F is also always negative. I do have a mnemonic in my head that I use to remember this, but I can't share it with you. You can probably figure one out yourself. So, the focal length is negative. What does that mean? So remember, in a concave mirror, there's a point where they don't form an image. Where is that point? At the focal length. Yeah, if you have a concave mirror and you put an object right at the focal point, no image is formed. Well, what about a convex mirror? Can you put an object at the focal point? No. So convex mirrors always form an image, and that's a critical difference. There is a point in a concave mirror when it magically disappears. That doesn't happen with a convex mirror. It's always going to form an image. But in a convex mirror, well, here's the question, and we'll answer it mathematically. Can a convex mirror form a real image? What do you think so far? Okay, let's do it mathematically and look at every case we can imagine. Now, obviously, we don't have all those same cases. With the concave, we have, well, object outside the center of curvature, object between the focal point and center of curvature, object inside the focal point. None of that can happen here, because every single thing is going to be on the plus side of the mirror, and the other things are all on the negative side of the mirror. So let's say that this is 10, making this 20, and I don't know that I'll even try a ray tracing, though. Well, proportionally it should work. And I will copy that. Darn it. I'll copy this so that on the next page we can, we'll just do that on here. Okay, so let's say that I place an object, and I'm going to make my object a little red pin, and we're roughing this out, but let's say that that's 10 centimeters in front of the mirror. It looks to be approximately 10 centimeters. Okay, so P, Q, F. What's my P? 10.0 centimeters. Q is what I'd like to know. What's my F? Negative 10.0 centimeters. So 1 over P plus 1 over Q equals 1 over F. 1 over Q equals 1 over F minus 1 over P. All right. Let me shrink some things. Got our numbers in. Now let's get a raw number for Q. Okay. What's your Q? Negative 5. Okay. So, where is this image forming? Behind the mirror. Yeah. It's a virtual image. So is your image in the bathroom mirror in the morning. It is a virtual image. The image appears to be behind the mirror. So, in rough, if we were to take a sort of a rough guess, we would say that the image should be, and we'll make it a sort of a faint reflection of this, somewhere in this region. Somewhere in there. Now, do we know yet if it is inverted or upright? No, but we can find that out mathematically very easily. Okay, magnification equals the negative of Q over P, negative of negative 5 over 10 equals what? 0.5, and we actually have, what, 3 sig figs, so 0.500 is our magnification. So, is this upright or inverted? Upright. Is it enlarged or reduced? Reduced. So what we should find in array tracing is that the top of the image is forming above the principal axis, and the height of the image should be smaller than the height of the object. So let's go ahead and get rid of everything else. Remember, this is not measured well, but it should be close enough to scale. Well, actually, let me just copy everything here. And we'll take this to the next page, and we'll do our ray tracing. And I'm going to enlarge this a little bit just for my own sake. I'm going to get rid of some of this stuff, because right now the numbers don't matter to us. And remember that that pink is just my prediction for where I think the image is going to form. We'll see how close we can get with this. Okay, so these are tough because the image is forming behind the mirror. So just like the concave ones where that image behind the mirror is always kind of a booger, these are too. So first ray goes to the mirror, parallel to the principal axis, reflects back, and I am going to label focal point, reflects back through focal point. So you have to connect this, this spot and this spot. So that gets us this. Okay. There's our reflection line, and it's our reflection line that we see behind the mirror. Typically, if you're doing this with a pencil and paper, we show that reflection line behind the mirror as broken. I'm not doing that so much on this, but I can, to show that there's no real ray, there's just the appearance of a ray. Well, so one thing is nice. At least our first reflection line behind the mirror goes through where I predicted our object would be. That's a good sign. So our second ray is going to go connect the object and the focal point inbound. And this will be a little bit challenging. I have to... Okay, so what am I going to do? I'm going to then mark those. If you're doing this with paper and pencil, it's pretty easy. With Doceri, because I don't want my inbound line to go behind the mirror, I just did that. Okay. Nope, that's no good. Okay, so there's my inbound line, and that has to reflect back parallel to the principal axis. So here's my reflection line, as close to parallel as I can get it. And if I imagine how that line would continue behind, if I show that as a broken line. So far so good. I've actually got two of my lines meeting right where I predicted my image would form. Now, my third line connects what two things? Yeah, center of curvature and the top of the object. So let me get my third line, top of the object, center of curvature, woohoo, bingo. Looky there, right where we predicted. And let me get rid of a few other bits of mess here. Is it as predicted above the principal axis? Yes. Is it shorter than the object itself? It's tough to tell because the scale's pretty bad, but yeah, it sure looks like it. It doesn't look like half to me, but again, we're not getting hard mathematical numbers here. We're getting a rough idea. And looking at this, I would definitely look at that and go, yeah, I'd say that that's smaller. Does that make sense? Basically, you're going to practice with these. So there are 6 problems for convex. Do them all. So this is page 540. And this is 14C, numbers 1 through 6. So for all of these, you also are doing array tracing to confirm your mathematical results. So it's good practice. We'll grade these on Monday. So basically the next 2 days we're going to spend just working on, I think you all have the math. The math is pretty like elementary algebra. I think the ray tracings are the tricky part, and remembering what gives you what information. Remembering, oh, Q, positive, negative, that gives me real versus virtual. So I think, and that's something you're just going to memorize. And you can write on your note card, positive Q equals What? Positive Q equals real. Write it on your note card. Negative Q equals virtual. Okay? Make sense? Good. Work.